Okay, so welcome back to the, was it 8th lecture now?
Yeah.
Of the cryptocurrency decal. So I'd like to introduce to you Aparna, who runs our education branch, and Don, who's going to be coming in at around the 30-minute mark, who does finance for blockchain at Berkeley. So this is actually the first time that Aparna and Don are giving a decal lecture. I know they've been working really hard on this. So please give your full attention to them as we continue to learn about alternative consensus and enterprise blockchain. All right.
Hi, everyone. Today's sign-in is going to be a quiz. That's why there's no code word. We are having a quiz because we haven't had one in a very long time. And second, it's a great check on learning. And you learn a lot by doing the readings. And the readings are the best way to really understand, not just by attending our lectures. So we want what's best for you. That's why we have a quiz today. Yeah. Okay, so let's get started. My name is Aparna Krishnan. Today I'm going to be presenting on alternative consensus and enterprise blockchain. Yeah. So when we talk about a distributed system, what are two important properties that ensure correctness? One is liveness. The second is called safety. Before we get into the formal definitions of what each of these mean, let's step back a bit and understand what is a state. A state is basically a condition at a specific period of time. So for example, what is the state of your bank account? Maybe it's like $0, you're in debt. Or maybe you have $10,000 in there. Yeah. So now let's take a look at the formal definition of both of these. Liveness basically means if the current state satisfies a liveness property, there's a state which satisfies the liveness property if there's a path from the current state to some future state where this liveness property also holds true. So a more intuitive definition of liveness is that something good will eventually happen. So for example, like a criminal will eventually be put behind bars, or in an Olympics race, an athlete will eventually win a gold medal. In consensus, specifically, it basically means that all processes or all nodes will eventually decide on a value. Notice that I've used decide and not agree because a node could wish something different but still conform to what is agreed upon by the rest of the network. Safety. So a formal definition for safety is that the current state guarantees the safety property if all the future states that can be reached from this state also satisfy the safety property. A more intuitive definition is that nothing bad will ever happen. For example, we desire a guarantee that an innocent person will never be jailed. Or we desire that if two countries sign a peace treaty, they will never go to war. It's something we desire that can be guaranteed. In consensus specifically, it basically means no two nodes will decide on two different values. Yeah. So this lecture, we're mainly going to be focusing on liveness and safety, but there's a theorem called the Fisher-Lynch and Patterson theorem, which states that it's impossible to achieve all three of these properties in any distributed system. Fault tolerance basically means that if any one node fails in a system, the rest of the system should not fail. But most of what we're going to be focusing on today is how to ensure liveness and safety in different consensus protocols. In an asynchronous distributed system, you cannot guarantee decisions and correct decisions at the same time. like within a time bound. You can only guarantee eventual decisions. So eventual consistency or eventual liveness means that everyone, all the nodes in the network have the same view of the values. So for example, in proof of work, it means all nodes in the network would eventually share one common view of the state of the blockchain. And this is because of the immutable nature of the blockchain, such that blocks are only appended at the end. You cannot reorder anything in the middle, or you can't mess with the transactions. Yeah. So two key consensus protocol problems are Sybil attacks and the Byzantine generals problems. Sybil attacks basically means flooding a network with false identities. In a Sybil attack, the attacker tries to subvert the reputation of a system or a peer-to-peer network by creating a large number of pseudo-anonymous identities. This allows the attacker to gain information by observation. The attacker's main purpose is to not create or flood the network. It is merely to gain information about the system and pass on wrong information to other nodes. Bitcoin is basically Sybil attack resistant. That's because of the proof of work mechanism, which we've been talking about so far. Today we're going to be talking about other consensus algorithms or protocols. A Byzantine generals problem is basically an issue of communication over an unreliable medium. So it goes to a story of a group of generals who encircle a city of Byzantine. And they're all trying to agree on a common plan, whether to all attack or all retreat. Everyone must perform the same action, because if they take a split action, that is considered bad, and that breaks the safety of the whole system. The plan of action must be reasonable and should be decided upon by gauging the size of their own troops and their enemy troops. An issue all these generals face is that they can only communicate with each other with the help of a messenger. They can't communicate in person. So another issue they face is that the decision of the honest generals in the network should not be impacted by the presence of a few traitor generals. However, if there's a huge split decision, then it means that there was no clearly reasonable decision that the network could make. In such a case, the traitor generals can greatly affect the decision of the network. So for example, if there are 9 generals, 8 honest generals and 1 traitorous general, 4 of the honest generals decide on attacking and 4 of them decide on retreating, the traitorous general could pass on the message to the attackers telling them to retreat, and the retreaters telling them to attack. This could compromise the security of the whole network. This is a nice analogy between the generals problem and Bitcoin nodes. Nodes can also be compared to computers in a network, but we'll focus more on how these nodes and generals compare in like nodes from a Bitcoin network. So for example, the good nodes are the truthful nodes in Bitcoin versus the generals, they're the honest generals or the loyal troops. An attack that, actually wait, can you see this down here? Is that better? Yeah. So an attack that the generals face could be a corrupt messenger, like traitors passing on wrong messages to the messenger. An attack that Bitcoin faces could be the 51% attack, or a double spend, or Sybil attacks, which we know can't really happen. All of which tries to add an invalid transaction to the blockchain. How do the generals solve it? Well, they don't really have a solution. That's why it's a classification of problems. Versus Bitcoin solves it with the help of proof of work. So one important property of all these Byzantine fault-tolerant problems is that they cannot guarantee safety and liveness if 1/3 or more of the generals are traders. So for example, in both these examples, Lieutenant 1 is honest. In example 1, Lieutenant 2 is a trader, and Lieutenant 1 cannot differentiate between if Lieutenant 2 is lying or passing on the right message from the general. In example 2, the commander is a trader, but Lieutenant 2 is passing on the honest message from the commander to Lieutenant 1. And yet, Lieutenant 1 cannot differentiate between who is the traitor in both these examples. So there's a discrepancy, and Lieutenant 1 cannot decide on one action. That explains why there's no way to eventually reach a consensus that breaks the liveness, and breaking the liveness and breaking the safety of the network. So in any BFT problem, only eventual liveness is possible because the lieutenants have to wait for messages that relay across the network. The number of messages that they have to wait for is equal to at least the number of traitorous nodes in the network. I haven't gone into too much depth here, but you can read more about it in a paper presented there. So, issues with Satoshi's proof of work. One is that it assumes majority of the computing power is held by honest players, and these honest players will execute the protocols correctly. Second, it claims that only 51% of honest majority is required, when in reality, because it's a class of a BFT problem, you need at least 66% of honest majority to be able to guarantee safety and liveness. Another issue with the proof of work is it's not great for enterprise blockchain apps. So that means all these apps need faster and cheaper settlement. If you go to a coffee shop and try to purchase coffee, but you have to wait 10 to 60 minutes for your transaction to be validated, you're going to get cold coffee. Another issue is it doesn't provide great scalability or performance, and any application that requires your identity to be verified cannot use proof of work. So today we'll be talking about other consensus protocols. All these consensus protocols can either be classified based on their mechanism, which could be like proof of work, proof of stake, PBFT, etc., or they could be classified as permission or permissionless, which basically means private or public. Today we'll be discussing proof of stake, ledger-based, federated consensus protocols like Ripple, and PBFT. So, proof of stake. A major assumption by proof of stake is that mining is done by stakeholders who have the strongest incentives to be good stewards of the system. So safety is guaranteed because someone with 51% or more stake has an incentive to do things that would benefit the system as a whole, as it will increase the value of the coins that they themselves hold. And you're assuming that nothing bad will happen and safety is guaranteed as long as this person who holds stake doesn't want to undermine the whole value of the currency and like launch a Goldfinger attack. If you guys recall, that's from lecture 6, where we talked about game theory network attacks. Liveness. So we'll talk about the mechanism Oh, did you have a question? Okay. Yeah. Liveness. We'll talk about the mechanism that guarantees liveness. So a group of validators are chosen randomly based on their coin ownership in this mechanism. So for example, if Alice invests 100 coins and Bob invests 200 coins in the proof of stake mechanism, Bob is twice as likely to be picked as a validator. What do these validators do? They create blocks and add in transactions from the pending transactions group into these blocks. Once these blocks are created, they have to be committed to the blockchain. The commitment of these blocks through the blockchain is done by signers. Different platforms have different signing mechanisms. For example, Tendermint requires every node in the network to sign off a block for it to be added to the blockchain, versus some other platforms just require a random group of nodes to sign off. These validators are paid in transaction fees or block rewards. Ethereum has a system where they generate all the coins at the start, so no more coins are generated, unlike in Bitcoin, where coins are going to be generated up to 2140. In Ethereum, they plan to have all the coins generated at the start, so that means miners are then only paid in terms of transaction fees, no block rewards. Purecoin was one of the first to implement a proof of stake and proof of work hybrid. Blackcoin, NXT also implement proof of stake. Ethereum plans to have this implemented by 2018. So some advantages of proof of stake is that it reduces electricity consumption, like by a huge amount. In Bitcoin, it takes about 10 gigawatt hours to create one coin. You could save that entire payment energy equipment cycle. You could remove that completely and use that electricity to do something else. Another advantage of proof of stake is that it assumes that the amount you gain is directly proportional to the amount you invest. So, like we talked about Alice investing 100 coins, Bob investing 200. If Bob is twice as likely picked as a validator, he's twice as likely also guaranteed to receive transaction fees when his block is committed to the blockchain. There's a reduced risk of centralization with proof of stake because you don't need ASICs to mine anymore. All miners can mine just as efficiently as one another. And it also gives miners a reason to be invested in the long-term health of this currency. Some issues with proof of stake is that it makes mining puzzles easier for those who hold more stake. So to incentivize those who hold more stake, incentivize people to hold more stake, it makes the mining puzzles easier for them, which is an issue. Another problem is dislodging a 51% par is impossible, which means if a miner has 51% stake, that means he's likely to be picked as a validator 51% of the time. And he can then just mine over his own blocks and get more transaction fees as rewards, thus increasing his own stake in the entire system. So his stake will eventually approach 100%, which is not good. Another problem is the nothing at stake problem, where so there's no penalty for trying to constantly fork this network. There's only rewards given to validators. So validators are constantly trying to fork the system. Don will talk more about this, specifically in Ethereum. Ethereum tries to get around this by locking up the funds of the validators, and if misbehavior is seen, it like slashes their funds. So another consensus mechanism is the practical Byzantine fault tolerance. It was one of the first few papers to be published in 1999 trying to solve the Byzantine generals problem by Microsoft Research. One assumption this consensus protocol makes is that the medium of communication is going to be reliable and that all clients are going to be responsive. Liveness is guaranteed because it assumes that all clients will eventually receive a reply to every request that they've sent, assuming that the network is functioning. Safety is reliant on the fact that the replies received by the clients are correct by vector linearization. The whole process of how this protocol works is a multi-stage process. It's useful in file servers and automated control systems. We'll take a look at how this works through an example. So if you have 4 clients or 4 nodes, replicas, whatever you want to call them, and they're trying to agree on one single bit, that is to either attack or defend. So each of them first votes on their decision. All the replicas or all the nodes then send their vote to every other node in the network. Once they have sent their vote, they vectorize the values from all the other nodes that they received, and then they send out the vector that they've generated to every other client again. And then the value that is most frequently appearing in all the vectors ends up being the agreed upon value. So we will now look at ledger-based consensus protocols. Paxos is one of the first ledger-based consensus protocols. So there are 3 steps in the way. There are 3 roles in Paxos, which assume safety. Paxos guarantees safety, but does not guarantee liveness. The 3 roles are 1, a proposer, an acceptor, and a learner. There's a 2-phase mechanism by which Paxos tries to guarantee safety. So in phase 1, a proposer sends a proposal with a unique serial number to the rest of the network. Each new proposal contains a serial number which increments. If an acceptor responds to the proposal he received, he promises to not look at any proposals with serial numbers less than the one that he just currently received. And then the acceptor responds with the serial number of the last proposal that was accepted by him. Not that he received, but note the wording, accepted by him. And phase 2, a request is accepted. The proposal with the maximum number of responses is then accepted by the entire network. So how does this guarantee safety? For example, if in round 1, the entire network has accepted a proposal with serial number 5, in round 2, suppose a node sends out a proposal with serial number 7. Any acceptor will respond back with the number 5 to him. So by doing so, like all the nodes in the network, like if proposal 7 then gets voted on to be the proposal with the maximum number of acceptances, then 7 becomes the new value which replaces 5 in the entire network. So anyone who now responds in round 3 will respond with 7. And that way there's no bad thing or discrepancy ever in the network. Everyone has one common view of the network. But it could take an infinite amount of time, and there's no guarantee on when this consensus will be reached. As I said, Paxos does not guarantee liveness. There are scenarios where you cannot reach a consensus, or it takes an endless amount of time to reach consensus. Some use cases of Paxos is Google uses Paxos in their log server, but as you all just saw, Paxos is very, very complex to understand and even harder to use and implement. So Raft tries to simplify this Paxos protocol and create a more understandable protocol to build off of. JP Morgan's Juno uses a Raft-based consensus protocol in their platform. So now we'll take a look at federated consensus protocols. One of the federated consensus protocols is Ripple. Ripple focused a lot on liveness and fault tolerance. Do you remember the triangle that we saw at the start? The fault tolerance, liveness, and safety triangle. Ripple does not care too much about safety. They only worry about liveness, which is eventually reaching consensus in a timed manner, and fault tolerance, which means any node in the network fails, the network shouldn't be failing. So how does Ripple do this? There's a worldwide shared ledger, which is created every few seconds, which keeps track of all the account balances. So it's sort of like a block which has all the account balances of the entire network. All the nodes in the network have to apply the same modifications on a set of transactions in the ledger that they have created. Transactions and proposals are so every node has a group of other nodes which they call their set of trusted nodes. So they match up any proposals they have received from their group of trusted nodes from any of the pending transactions. And if there's a match, they vote for it. At the end of each round, there's a timeout. At that point, any proposal with more than 50% votes will move on to the next round and will become another proposal. And it's an iterative process which goes through timed rounds until any one proposal reaches over 80% of votes, at which point all the nodes in the network will update their ledgers to have the same modifications of transactions. The safety relies on the assumption that a node which does not have the same changes as the majority is going to update its own ledger to whatever was agreed upon by majority. And it also assumes that the network is closed and no external nodes are going to join the process during consensus. Ripple has a great use case in the banking industry. Yeah. Stellar is a fork of Ripple, which started off in 2014. So as you recall, Ripple didn't focus that much on safety, which led Stellar to be more stringent about their safety and focus less on their liveness. So Ripple has timeouts. Stellar doesn't have timeouts. Stellar is like a divergent state occurs when ledgers hold different nodes stored by contradictory states, and Stellar thinks that a blocked system, or a system which doesn't achieve consensus in a certain amount of time, is less dangerous than a divergent system. So a system where each node has a different view of the network is the most dangerous, according to Stellar. Some advantages of Stellar and Ripple consensus protocols are that they don't need centralization. There's no central party that's required to authorize consensus. They're both low latency, which means they can achieve consensus in about like 5 to 10 seconds as compared to proof of work, which takes at least 10 minutes. And nodes can trust any set of individuals. They don't have to trust their entire network. So, for example, in Stellar, if this is a set of nodes in the network, V1 can choose to trust V2 and V3 without saying it trusts V4. But V2 trusts V4 and V3. V3 trusts V2 and V4. Thus, V1's decision is eventually impacted by V4's decision, but V1 doesn't have to directly trust V4. And if a node doesn't vote or want to decide, its decisions is made by the nodes that it trusts. Yeah. So now we'll see some quick use cases of enterprise blockchain. Enterprise blockchains are classified as permissioned or permissionless. Permission means private, permissionless means public. Some broad use cases of enterprise blockchain are payments, transactions, processing, and settlement. Under payments, blockchains can be used as peer-to-peer lending and crowdfunding. If you've heard of WeTrust, they tried to build a lending community such that you lend within your family and your friends using a blockchain. Bank of America was trying to use a blockchain and do something with trade finance. Yep. Other possibilities to use a blockchain are microtransactions, online gaming, decentralized energy transmission and distribution. Microtransactions are possible if there's no transaction fee. Asset management and blockchain can be used for IoT supply chain management or online storage of information or files, which is what IPFS does. They're a company called Interplanetary File Storage Systems, and you should check them out. They're pretty cool. Other use cases of blockchain are for voting or proxy identity and anti-counterfeit. All this is possible because blockchains are immutable. Now, Don will talk about some of the very important platforms in blockchain.
Need a microphone. All right, I'm going to give a more broad overview of two specific platforms and then touch upon another one. So HyperLedger and Ethereum. So HyperLedger is focused around interoperability, security, and performance, and I'm going to show you how. So why do the creators of HyperLedger decide that we needed a solution, or what were the problems that they were trying to solve? So number one, we live in a world where many different people have different types of networks and different systems, and they don't exactly mesh well together. Imagine Bank of America and Chase using different software, and what HyperLedger is trying to do is allow these two different parties with different software to interact in a reliable manner. So there's also an increased demand for permission networks. We kind of discussed this a little bit earlier, and the importance of both privacy and confidentiality. Okay, so HyperLedger is basically, it's an open source collaborative effort. It's trying to advance cross-industry blockchain applications and technologies, and it was hosted by the Linux Foundation, but the companies like IBM are also a big part of this. And so it spans things from finance, banking, IoT, supply chain, which by the way is if I'm producing rice, and so yeah, supply chain. If I'm a rice producer and I want to know how much rice goes on the conveyor, and like that's kind of what I mean by supply chain. Yeah, manufacturing and technology. So touched upon this earlier. The goal is to create an enterprise-grade, open-source, distributed ledger framework and code base upon which users can build and run robust industry-specific applications, platforms, and hardware to support business transactions. So what's the difference between HyperLedger and existing blockchain technology? Well, I'm going to compare HyperLedger to Bitcoin because Bitcoin is something that most of you are probably pretty familiar with. So using the example of Bitcoin, let's look at limited throughput. So Visa as a transaction or as an entity, they can process more than 3,000 transactions per second. In contrast, Bitcoin is only 7. So you can see that that's 3 orders of magnitude. It's a pretty big problem. So this is something that HyperLedger is trying to address. Slow transaction confirmations. If you guys are, again, I'm going to bring it back to Bitcoin. If you're familiar with Bitcoin, a block is supposed to be produced every 10 minutes, right? And every 10 minutes, you're supposed to get, so if I were to transact with Ronan, what's supposed to happen is within 10 minutes, my transaction is supposed to be confirmed at least once. But blockchain is having, or Bitcoin is having problems actually even confirming on the first block. So since the block is actually getting full, we need solutions like SegWit, etc. But it can take up to 400 minutes for confirmation on the blockchain network, and this is simply not acceptable. So settlement finality. What this means is, if I transact with Aparna, I want to know, and she wants to know, that so if I give her 10 units of currency, she wants to know that that can't be taken back retroactively. In effect, that I can't double spend. And this is a little bit of a problem. In Bitcoin's case, in 2010, an attacker managed to give themselves 186 billion Bitcoin by exploiting an integer overflow vulnerability. And this was fixed, but at the cost of reverting half a day's worth of transactions. So, yeah. Another example, in 2013, the blockchain forked because of a bug that existed in one version of the software, but not another version, leading to part of the network rejecting a chain that was accepted as dominant by the other part. And this took, again, 6 hours to resolve. And in 2015, roughly 6 blocks were reverted because a Bitcoin mining pool was mining invalid blocks without verifying them. So this pool was selfishly mining. And so settlement finality is only probabilistically, it's not like a concrete thing. So they're trying to address this. And I think the most important part is Bitcoin was never designed to be like a generalized blockchain solution. It was designed to be a currency first and foremost, or maybe you could argue a store of value. But all of these different things like IoT, supply chain, they need something that wasn't developed to be a cryptocurrency, something that can work in whatever use case. And poor governance. So an example of this is just so I briefly touched upon SegWit earlier, segregated witness. This is something that Bitcoin is trying to get adopted, but it needs somewhere around 95% consensus, and so far hasn't been able to do that. So important changes that are necessary for the infrastructure and integrity of Bitcoin are not happening because of poor governance. We can't get an agreement. And finally, fungibility. This is very closely tied with the issue of privacy. Fungibility essentially means that if Aparna has 10 Bitcoin and I have 10 Bitcoin, my Bitcoin are worth the exact same amount as hers. And you might be wondering, in what scenario would my Bitcoin be worth less than hers, right? Well, say I have some, I don't know, let's say I have some, I have Bitcoin and they have a certain amount of taint, right? So I don't know if you're familiar with taint. Taint is basically Bitcoin that have been involved in either illegal activity or something that's not condoned by whatever authority, right? So if I have 10 Bitcoin and like 50% of them are tainted and hers is like perfectly clean, basically my money's worth less in effect. So privacy solves this fungibility issue, and yeah. So the scope of the HyperLedger project. So I was talking a little bit earlier about how Bitcoin is a very specific use case for blockchain tech. And we can see like custom applications, which would be like Bitcoin or any of the distributed apps you might develop on Ethereum's platform, or any other just cryptocurrency or whatever you can imagine. That is out of the scope of the HyperLedger project. Basically, HyperLedger is trying to develop a code execution environment as well as certain data structures. And one of the most important things that I want you guys to take away with you is this concept of modularity. So we talked briefly about okay. So yeah, imagine you don't really need privacy, right? You can have, if some institutions might need that, and the idea basically is if I don't need privacy in my blockchain, I can have that as a modular thing. I can either include it or I don't have to. Also, HyperLedger is not tied down to one specific consensus algorithm. If I like proof of stake more, or if I like proof of burn or proof of like space, then basically I can switch those out, and they're different modules. So that's kind of the focus of HyperLedger. Okay, I'm going to briefly go over Ethereum. So it's created in 2013. It's pretty mature with many applications already built, and currently in blockchain we work with this a lot. So yes, it's a Turing-complete programming language, and a large number of users secure the network. But the cons, in contrast to HyperLedger, it has a defined consensus protocol. So let's talk about that consensus protocol. Ethereum is going to switch over to proof of stake in the near future. I believe in 2018 is when that's scheduled. So why are they switching to proof of stake? Well, proof of stake has benefits over proof of work in that there's no need to consume large quantities of electricity in order to secure a blockchain. And because of this, the lack of high electricity consumption, there is not as much need to issue as many new coins in order to motivate participants to keep participating in the network. So it may be even theoretically possible to have a negative net issuance, which means we can implement this through proof of burn, where a portion of transaction fees are burned and the supply and the total currency goes down over time. So who here has heard of economies of scale and maybe could give me a brief explanation of what that means?
Average fixed costs go down the more you produce. So like telecommunications companies are huge economies of scale.
Right, perfect. So the way that ties into Bitcoin is currently, it takes a lot of research and development to make ASICs, which mine Bitcoin. But the difference is with proof of stake, you don't need that kind of hardware. So this means reduced centralization risks, as economies of scale are much less of an issue. $10 million of coins gets you exactly 10 times higher returns than 1 million in coins, without any additional disproportionate gains because at the higher level you can afford better mass production equipment, like ASICs. Finally, ability to use economic penalties to make various forms of 51% attacks vastly more expensive to carry out than proof of work. And Vlad Zemfir, basically, it's just not a good idea because you have a stake in the network, and if you're messing with the network, you're messing with your own stake. So continued. The CAP theorem, CAP stands for consistency, availability, and partitions. So you can pick two of these three things. So in the case that a network partition takes place, you have to choose either consistency or availability. You cannot have both of these things. So yeah, also another issue is that as network latency increases, fault tolerance approaches 0. So imagine if we're all nodes in a network. If we cannot communicate with each other, there's no way we can reach consensus. Okay, I have about 3 minutes. So let's talk about the nothing at stake problem, which Ethereum aims to solve. But it's a good idea that you know why currencies like Peercoin, which were the first to implement proof of stake, have not taken off. So we can imagine two forked blockchains. One has a proof of stake style consensus algorithm, and the other is proof of work, maybe Bitcoin. So under proof of work, what happens is you either have to pick one chain or the other, so either A or B. So if you pick A, so we're looking at the bottom. If you pick A for proof of work, your expected value is 9 or 0.9, because that's the probability that that chain will be adopted by the network. But you see, you cannot pick both because you have to dedicate some mining resource in order to vote effectively. This is not a problem with proof of stake because there is no mining going on. So you can effectively vote on both of these things and get return from both of them. So this is an issue. Yeah, so there's no miners but forgers. An ID and a public key are used to seed a random number n. This is in proof of stake. N multiplied by the amount of stake that you own, the amount of coins, multiplied by the amount of seconds since the last block. If this is greater than a threshold value, then you can create the next block. This is how proof of stake works. But the problem arises if two forgers arrive at the threshold at a similar time, we get a fork. And usually forks are resolved by majority picking one chain, and the block on the other chain gets orphaned. And yeah, I touched upon an interesting property, is that because there's no resource being used, you can basically vote on both at the same time. So some argue that stakeholders have an incentive to act correctly and only stake on the longest chain in order to preserve the value of their investment. But this suffers from the tragedy of the commons problem. And if you're trying to imagine what tragedy of the commons means, I think the best example is basically like global warming. And I promise I'm almost done, guys. So yeah, if tragedy of commons is an economic theory or a situation within a shared resource system where individual users acting independently according to their own self-interest behave contrary to the common good of all users by depleting or spoiling that resource through their collective action. Again, global warming. So we can solve this. If you want more details, please talk to me after class. But we can basically solve this by implementing, or we can punish validators for creating blocks on the wrong chain. So basically the idea is we want to take proof of work economics and apply them to proof of stake blockchains. And yeah, R3, the most interesting thing about this is that they were trying to tie smart contracts to the law. And they're defunct now, but that was, yeah. So thank you guys.